All right, kiddos, we're back and we're going to learn about binomial probability today. And you might wonder why binomial might be helpful for us. I don't know if you remember back in drawing all those tree diagrams. Binomial is a shortcut for most tree diagrams. So you'll hopefully like that. You will want your calculator handy. I'm going to teach you a few new things on that. So if you need to pause the video and go get your calculator, please do so. All right, so binomial is a process that works for specific types of cases. What I mean by that is back when we were learning tree diagrams, we had a couple different scenarios. You could have independent events or dependent events. Well, binomial only works if the events are independent. So you still have to know how tree diagrams work for all those cases where the variables are dependent, okay? So it's still important to know tree diagrams. But for binomial, we can shorten it if they're independent. We have to know how many times the trials are performed. So are we flipping a coin 3 times? Are we flipping a coin 4 times? Just different things like that. The trials have to be either a success or a failure. It can't be outcomes like red, blue, green. You can't have 3 different things going on. It either is a success or a failure, okay? The probability of success on each trial is a constant, and the probability of failure is always going to be 1 minus p, okay? And that's pretty much, we won't run into too many problems or too many issues with that. So you probably recognize for the formula this part, because we've been using that a lot with combinations, okay? But the rest of this looks a little bit unique. So let's just go over what the variables mean. The p here means the probability of success, and here is the probability of failure. Now, each of these other pieces, notice how the r just gets shifted and put right there as an exponent on the p. And then this ends up having an exponent of n minus r. Okay, so we'll go over, hopefully it'll make a little bit more sense when we start this. I am going to skip through these first couple slides on the basketball, Carl Anthony's free throw, and I want to get right to this one because it's going to help me explain why it's related to tree diagrams and how it's kind of a shortcut for it. So first, this problem says when people go to an animal shelter to choose a cat or a dog, the probability that the person will choose a dog is 0.57, and the probability that they will choose a cat is 0.43. And a family has 3 kids, and each kid will be choosing a pet. First of all, this family is incredibly kind. To let all of their kids choose an animal on the same day is just a crazy thought. So this problem says, what's the probability that exactly 2 of the kids choose dogs? Well, let's just highlight all the branches that work for that situation. 2 kids choosing a dog. So this branch works, right? Or I can go over this one again, cat and then dog. Or if they choose a cat, first kid chooses a cat, next kid chooses a dog, and the last kid chooses a dog. So there's 3 different branches that work. Now you probably agree, because you've done enough with tree diagrams, to know that if I were to take any one of those branches and multiply for the probability, we would get the same probability for all 3 of these. And the reason being is you're multiplying the same numbers just in a different order each time. So it ends up being about, after rounding, this for each of those branches. And then what you would have done is you would have said, okay, 0.140 times 3. So we would have gotten a probability of 0.42. Okay, we answered the question. That was the old way, but can we get around that by just doing a shortcut? And you can. So first of all, I want you to think about how many branches worked, or how many branches did we need to use? Well, we had 3 that worked. This one, and this one. So there are 3 branches. Okay, so we needed to get 3 branches, and then to get the probability of each, we had 0.43 times 0.57 times 0.57, and 0.57 can be, when you're multiplying these 3 things, you could combine 0.57 times 0.57 and just write 0.57 squared. So when you look over here at the new way of solving this, can you kind of understand where they're getting 0.57 squared from? Because there's twice. And then we only have 0.43 once, so that only has an exponent of 1 on it. But we also have this piece of 3 choose 2. Now, if you type 3 choose 2 into your calculator, you get an answer of 3. And remember how I said we need to take the number of branches times the probability of all those branches? Well, this gives you the number of branches. And these two items give you the probability of the branch. Therefore, next time we solve this problem, we actually don't even need all of this stuff over here. We could just do this instead. I don't know if that kind of makes sense. So let's try it on a new problem, okay? All right, so it says a Major League Baseball player has a .295 batting average. And then it says, what is the probability that he gets a hit in exactly 4 of his next 10 at-bats? So let's set up the combination part. We don't care the order that he gets hits in. Could be the first and the second hit and the last 2, or it could be the middle 4 or the last 4. It doesn't really matter. All we know is he's going to have 10 at-bats, and we want to choose 4 different times that he gets hits. Now, the probability he gets a hit, which is considered to be the successful probability, so this is the probability of success, or the p-value in our formula, is going to go next. So the probability of success is 0.295. And how many times did we want him to experience success? Well, we wanted him to have it 4 times. Okay. And then you're probably thinking, well, what's the probability of failure? Well, probability of failure is we're just going to do 1 minus the 0.295. So that gives us a probability of 0.705. And if we wanted 4 successful attempts out of 10, to get the probability of failure, I want to do 10 minus 4, or 6 attempts. So I'm going to rewrite this. This is really what I'm solving for. Now what we're going to do is we're going to put all of this in our calculator all at once. Okay, so to give you a little bit of an idea of what that looks like, you enter the choose like I always taught you to do. So it's going to look kind of like this in your calculator, especially if it's the older version of calculator. And then you're just going to say 0.295. You could have a multiplication sign in between there. And then you're going to do the exponent. Okay, so that's how I'm going to enter it in my calculator right now. And I hope that kind of helps you figure out what it's going to look like. You can type it into your calculator at home to make sure you get the same answer as me as well, to the 6. So it says that this batter has a probability of 0.195 of hitting exactly 4 out of the next 10 at-bats. Let's try another one. A local tuxedo store rents 65% of their tuxes to high school students. What is the probability that exactly 7 of the next 11 purchases are made by high school students? So this looks like the probability of success. And so to start it off, I'm going to say there's 11 people that we're looking at. We want to choose any 7 out of that to be high school students. We don't care the order. That's why we're using combination. Then I'm going to do the probability of success, and I want it to be successful 7 times. I want 7 high school students. So then the probability of failure is going to be 1 minus 0.65, which is 0.35. And how many times do I want it to be failure? Well, if 7 out of the 11 attempts were successful, then 4 would be failure. So I'm going to put all of that into my calculator in one long line. Maybe I should write that out again, how I would enter that. Give me just a second, and okay, so I would say 11. That caret key to get the exponent. That's what I'm entering. So I get a total of 0.243. and that's a probability. All right, so this is going to kind of show you what happens as we increase or decrease. So it says in this problem, Mrs. Wiitala's free throw percentage is 0.89. It really isn't. This is totally made up, I guess. Mrs. Wiitala shoots 5 times. What's her probability that she makes 0 shots, 1 shot, 2 shots, so on and so forth? So this is setting up a binomial for all situations here, okay? So just think about it. If you have a free throw percentage of 0.89, you're likely to make more shots out of 5. So is it very likely that I'm going to miss all of them? Like I'm going to take 5 shots and I'm not going to get any, 0 of them. Well, if my free throw percentage is that good, that means that it's going to be a really low probability, okay? However, if you go on the other end of that, since my free throw percentage is really good, if I take 5 shots and I make 5 shots, that's more likely to happen. In fact, it's more than 50% chance that it's going to happen, okay? Now, this covers all the scenarios of me making 0, 1, 2, 3, 4, or 5 shots. So what we need to do, or something we need to consider here, is just thinking about how these all relate, okay, right? In a tree diagram, when you had those, you could take and add up the probabilities of all of your branches, and they should total to equal 1. Well, since we're dealing with situations that are similar to a tree diagram, if I were to take all of these numbers and add them all up, it should equal 1. Now, in this case, do they actually equal 1? Maybe not because of my rounding that I had to do with some of the decimals, but it should be really, really close to 1. Okay, again, because it's related to a tree diagram. So instead of watching me painfully calculate these over and over again, we're going to use these values here to discuss the next couple problems. First one says, what's the probability Mrs. Wiitala makes exactly 3 shots? Well, setting that up, I was still shooting 5 times. I choose 3. The probability of my success rate, or my free throw shot percentage, was 0.89, and of me missing it, or the probability of failure, is 0.11. And so we can just look over here instead of me entering it into my calculator all the time, and I can see, yeah, that those match up, right? So that's how I get that probability. But now they're going to change it up on us, and it wants to say, what's the probability she makes 3 or 4 shots? That means I have 2 situations. I could make 3, and it would be the same setup as the problem above, or, which means I'm going to add, I could make 4 shots. And if I make 4 shots, it changes the exponent on here to be a 4 and the exponent on here to be a 1. Now, if I add those together, I'm going to end up getting, where, let's see here, 3 was 0.085 plus making 4 is 0.345. And so I'm going to want to, oh, I keep doing that. I'm going to want to add those ones up. Okay, so 0.085 plus 0.345. All right, so I get a total of 0.43. That's the probability. Next one says, what's the probability Mrs. Wiitala makes at least 4 shots? That means 4 or more shots. So that looks like I'm going to use this situation, and I'm going to add it to this situation. So just to make it shorter, I would add both of those. Now, I'm going to tell you, when you're doing these problems, I'm not going to have this fancy table all prepped for you. So you're going to have to do the multiplying and setting up in between there. So this is the probability that I make at least 4 shots. So then the last one on this page asks, what's the probability that Mrs. Wiitala makes at most 1 shot? So at most means I make 1 or less. So that's these 2 situations here. So I would add the 0.000. I'd add all those up. Which doesn't that just end up being something like that. All right, let's see what else we have here. All right. So 2 more problems left. It says an unfair coin has a 48% chance of landing tails and 52% chance of landing heads. Find the following. All right, so when we start out this one, probably of at least 1 head out of 12 flips, okay? That means it could be heads once, heads twice, heads 3 times, 4 times, 5 times, 6 times. Okay, so that's going to be a lot of work because what I'm thinking in my head, and you don't have to write this down, but I'm thinking out of 12 flips, I have to do 1 head with all of that other work, right? Plus 12 choose 2 with all of that, plus 12 choose 3 with all of that, and it's going to take me forever to solve this problem. So instead, let's think about another way around it. We know if we added up all of the branches in a tree, it would add up to be 1. We could then say, what's the one branch in this situation that wouldn't work? Well, if we need at least 1 head out of 12 flips, 12 choose 0, or getting no heads, is the one situation in the whole tree diagram that's not going to work. So instead of adding up 11 different options, I could just take 1 minus the one option that doesn't work. So I have to be careful about this because we're saying 1 head. So we're saying this heads is successful. So we have to write down this was the chance of it landing on tails. This is the chance of it landing on heads. The 0.52 is going to go here. And we want that to happen 0 times. And the 0.48 goes here. And we want that to happen a total of 12 times because we want all those flips. So I'm going to put that in my calculator. I'm just putting in like normal 1 minus 12 choose 0 times 0.52 to the 0 times 0.48 to the 12th. And I'm going to end up with 0.99985. Okay. So it's not very likely, right? Or yeah, it is very likely that you're going to flip at least 1 head out of 12 flips. It would be unlikely, even though the coin is weighted or whatever, to get all 12 to all 12 to be tails is basically what they're saying. All right, then the next one says the probability of at least 2 tails out of 10 flips. Okay, so again, this is kind of irritating because you're like, well, thinking it could be 10 choose 2, and then it could be 10 choose 3 with all of that stuff, and it could be 10 choose 4, and you're going to have to do that all the way up to 10, and that's going to be really irritating, right? So we should look for a shortcut again. I'm going to do 1 minus, except I'm going to subtract more this time. There's 2 situations that won't work. We need at least 2 tails. Well, that means that if I have 10 flips, no tails doesn't work. So that's why subtracting it from 1 helps us. Or 1 tail doesn't work. So now I'm going to set it up, and I have to be careful because this one was asking for heads as the thing of success, but this one's saying tails is now the success. So I'm going to list 0.48 here and 0.52 next, and we want 10 of those, and 0.48 here with a 1, and 0.52 then with a 9 there. Okay, so I'm going to put it in my calculator just like that, and it does help. You will need these parentheses here because of that addition sign above that arrow. Otherwise, if you don't have that, it won't give you the right answer. 0.4. This might just take one moment. Okay, whew. After all of that, we get 0.015. It's 47 after that, but I'm going to round it to 5. Okay. Again, binomial is a shortcut. These problems don't seem too short, but it is a shortcut for us still. All right, I think this is the last. So In a hospital, 60% of patients are dying of a disease. Okay. This is not the best problem I'm looking at just because of what we're dealing with. If on a certain day 8 patients got admitted to the hospital for that disease, what are the chances that only 3 survive? I just don't think this is a great problem for the times. We're gonna skip this problem. The homework assignment is the binomial probability worksheet. If you have any questions, reach out to your teacher.